Hey, this is Horner. We're going to look at number 36 for the AP Physics C rotational motion pretest. And here we've got two objects. One is 6 kilograms, one is 8 kilograms, and they're hung from this stick, which is 70 centimeters long. It's got marks every 10 centimeters. The mass of the stick is negligible, so you don't have to worry about it. They want to know at which of the points indicated should a cord be attached to the stick so it will remain horizontal. Because we have a larger mass on this side, we know that we need to have something to the right of our center. So we know that we can't pick A, B, or C, so now we're left with D or E. Just by inspection, you'll notice that the masses are not vastly different. And if they're not vastly different, probably the best answer to pick would be D. And D would be the correct answer. If you really wanted to do this and use torques, you sure could. And you would find out that your X value for position should be at D. But I think this one you can just do on just an inspection, just kind of looking at it. For number 37, you have a 2 kilogram object that moves in a circle of radius 4 meters at a constant speed of 3. There's a net force of 4.5 newtons that acts on the object. They want to know what is the angular momentum of the object with respect to the axis perpendicular to the circle and through its center. So for this one's really not bad. In fact, it's pretty easy to do. The key here is they give you a force that you don't need. And angular momentum, we've talked about it a couple of different ways. The one way to do it is mvr, and then you can just calculate it from this. So our mass here is 2 kilograms. We know our velocity is 3, and then we know that the radius of the circle is 4. So 4 times 3 is 12, 12 times 2 is 24, and that would be our answer. For number 38, we've got a wheel of a radius r with negligible mass. So you don't have to worry about the mass of the wheel, which is kind of funny. It says it's on a horizontal frictionless axle so that the wheel is in a vertical plane. 3 small objects having mass m, big M, and 2 big M, respectively, are mounted on the rim of the wheel if the system is in static equilibrium. So we know that the sum of the torques for this thing should be equal to 0. So we need to just figure out which way is this thing going to torque as we go. For the 2m mass, we know that it would go this way, so that would be a negative torque. For both M and big M, we know they'll both go this way, so we know that this is going to be a positive torque, and then this one will also be a positive torque of some type. Now we can go ahead and solve. So let's take a look at this one. For number 38, we need to know the net torque. So let's do that first. The clockwise torque, so our clockwise torque here is going to be 2 times big M, and then we have to multiply that times our radius. And so here we see this R is here, so here's our radius right here. So this would be 2 times M times R, but it's not just M, we've got to have a force, so that we're going to have to put our G in there. The counterclockwise torques are going to be big M times G times big R, and little m times G times big R again also. So now that we have those, we should be good. The only problem we have with this one is it is at an angle, and we've got to figure out what would it be if it was perpendicular. If it was parallel to this line. So at this point, we need to also make sure that we have cosine of 60 degrees. So that would give us this side. That would give us this side. So we're thinking about the tangent. Now that we have that, we can go ahead and plug everything in. So at this point, we have 2mgr is equal to little mg big R plus 1/2 of big M times G times big R. And so let's do a little bit of math here. We'll get rid of the G's. We can also get rid of the radii. And now we want to solve it for little m. So little m here is going to be equal to, we're going to have to subtract, we're going to have to move that over, move this one over here. So now we've got, instead of just 2, we're going to have 4 over 2. And then we still have the m on this side, so we had to subtract this from both sides. So this would be 4 over 2 big M minus 1/2 big M. And so now we're left with our answer, which is 3/2 big M. So little m is equal to 3/2 big M, or 3 big M over 2, and that's number 38. For the next question, which is number 39, I have a rod on a horizontal tabletop. Here it's pivoted at one end, free to rotate. The force is applied to this end at an angle right here. If F were applied perpendicular to the rod, at what distance from the axis should it be applied in order to produce this same amount of torque? So for number 39, by definition, we know that torque is equal to R times F times the sine of the angle. So in our case, that torque would be equal to LF times the sine of the angle. If I do this perpendicular to the surface, then we really would just have some distance x times f, because sine of that 90 degrees would be 1. So here we're going to have to say that our answer should just be L times the sine of the angle. So if we kind of go back here, we know that torque is equal to LF sine of the angle. Okay, we could solve this for x if we know that since torque is equal to xf and torque is equal to this, if we solve for x, so we can kind of just say xf is equal to L times f times the sine of the angle. If we cross off what's the same on both sides, our position now will be equal to L times the sine of the angle. And so that's what we need here. So now we are set with number 39. For number 40, this one, it says you have a wheel rotating about a fixed axis, has an angular acceleration given by this, where theta is measured in radians and t is in seconds. They want to know what is the angular acceleration of the wheel at t is equal to 2 seconds. So for this one, the first derivative would give us the angular velocity. So we really want to go ahead and do the second derivative, which would give us angular acceleration. If we do the first derivative, we're going to end up with 3 times 2 is going to be 6 t squared. And then if we do the second derivative of this, so this 3 goes away, if we do the second derivative, it would be 12 times t. And so we're going to take 12 times 2, and that would be 24 radians per second squared. So this answer's got to be B. Notice that it is negative, okay, and it's negative because we've got our negative value here, so really we probably should have left those. So negative 12 times that 2 is going to give us negative 24 radians per second squared. And that is the end of number 40.